Hi everyone, welcome once more to this YouTube channel, tutorial channel at Best Science Brain YouTube channel. Today we are taking a look at a topic in physical chemistry. We are looking at the effect of temperature on the reaction rate. So if you are not subscribed to this channel, kindly move up to the channel's name, Best Science Brain. Close to the channel's name, you see the subscription bell or icon, a tiny bell. Tap on it only once and get subscribed to the channel to be seeing our video notification from time to time as we teach general chemistry and general physics, both for O-level and for high institution. So today's lecture is meant for those in high institution, particularly students in the second year of chemical sciences, chemistry, microbiology, engineering, and other aspects of sciences that require physical chemistry as their coursework. So today, as I said, we're looking at the effect of temperature on the reaction rate or rate of chemical reaction. So we know that increase in temperature leads to increase in the rate of chemical reaction. If you increase the temperature of the reaction system, the molecules or the reactant molecules will gain sufficient kinetic energy and they will start moving faster. So, as increased temperature, reactants will have higher velocity and will start moving faster. As they move, they collide with each other and with the walls of the container. That means the frequency of collision between the reactant molecules will increase as the temperature is increased. And the higher frequency in the rate of collision leads to a higher rate of chemical reaction. So we read what we have. It says the average kinetic energy of molecules increases with an increase in temperature. Hence, the number of molecules with energy greater than the threshold energy also increases. Consequently, the number of effective collisions between reactant molecules also increases. Therefore, it is usually observed that the rate of reaction increases with increase in temperature. So as we explained before, if you increase the temperature of the reaction system, the molecules will gain higher kinetic energy, and then that results to a higher rate of collision or higher frequency of collision between the reacting molecules and the walls of the container. And unless there is collision, there will be no reaction. So the higher the number of collision, the greater the tendency for the molecule to have effective collision. It's only effective collision that leads to reaction. Effective collisions are those collisions that occur when the reactant molecules possess the minimum activation energy required to form product. So the effect of temperature on the rate of reaction was studied by a man called Arrhenius. He gave us the famous Arrhenius equation. So let's continue the second paragraph. The relationship between reaction rate, absolute temperature, and activation energy given by Arrhenius equation, which is given as K equal to capital A exponential of minus EA over RT. So what do those symbols stand for? K is specific rate constant or rate constant. A is called the frequency or the collision factor. EA is the activation energy. And R is the gas constant. So it's a constant. The value of R can be 1.987 kilocal per mole per Kelvin, or R can be given as 8.314 joule per mole per Kelvin. So second value of R is expressed in 8.3 in SI unit, while the first value is expressed in calorie in non-SI unit. So, and then capital T is the absolute temperature for that equation. So having done that, we'll now go to that equation and we'll take natural logarithm on both sides of the Arrhenius rate equation. Natural log, or which you can call ln, lean, pronounced as lean. So we have that L in front stand for logarithm and N natural. So taking the lean on this Arrhenius equation, the lean on the right hand side, we now have lean K equal to lean A minus EA over RT. So when you take lean, the exponential symbol, that small letter e, will be removed. So you now have minus EA over RT. So that becomes equation number 1. So having done that, we'll convert this equation 1, that is this natural log form of Arrhenius equation, we will convert it to log to base 10. So it reads converting natural logarithm to logarithm to base 10. What relationship? Natural log S or ln S is equal to 2.303 log S. So where we see ln S, replace it with 2.30 log of the value. So ln K replace with 2.30 log K, and then ln A replace with 2.303 log A minus EA over RT. So we have transformed the natural log form of Arrhenius equation to logarithm to base 10. So what then do we do? We divide both sides of the above equation with 2.303. Dividing both sides with 2.303, we now have we have log K equal to log A minus EA all over 2.30 RT. That's equation 2. How do we get equation 2? Go back again. Look at this expression. Divide both the left hand side and the right hand side with 2.303. So divide 2.303 log K by 2.303, you have log K. Divide 2.303 log A by 2.303, you have log A remaining. Divide EA over RT by 2.303, you have that expression EA all over 2.303 RT. That becomes our equation 2. You can see that. So, having done that, let us now consider the equation of a straight line and compare with the Arrhenius rate equation. A straight line equation given by y equal to ms plus c. That's the equation of a straight line, y equal to ms plus c. Now we'll bring the Arrhenius equation down, but in a rearranged manner. Log k equal to, we swap, we bring minus EA all over 2.30 RT close to the equality sign, as you can see there. And we shift log A behind minus EA all over 2.30 RT. You can see that. We just rearrange it. So having done that, then equating variables, you see that y in the straight line equation corresponds to log k. And then you see that s in the straight line equation corresponds to 1 over t. Then if you remove 1 over t from minus EA all over 2.303 RT, remove 1 over t, what remains now is minus EA all over 2.03 R. So minus EA all over 2.30 R now will correspond to m, which is the value close to s. And that m is the slope or gradient of the straight line equation, as you can see. Then you go back to the straight line equation. what remaining is C, that is the intercept. So C now correspond to log A. So go down. C is the intercept on the vertical axis, and that is log A. So if you plot a graph of log A on the vertical axis, if you plot a graph of log A on the vertical axis against 1 over t on the horizontal axis, we have a straight line graph. Again below, log k over 1 over t, we have a straight line graph, where, as we say, the intercept on the vertical axis is log A, you can see that, and then the slope is minus EA all over 2.303 RT. So in this lecture, we are not going to the graphical application of this Arrhenius equation. We are not plotting graph. We are looking at the quantitative treatment, the calculation aspect of this Arrhenius rate equation. So now go to calculations on Arrhenius rate equation. So how to perform calculations on Arrhenius rate equation? So to perform calculations, there are certain things we have to know. So let's see. Let us consider the logarithm form of Arrhenius equation for two sets of conditions for a given reaction with specific rate constants K1 and K2 and temperatures T1 and T2. So we are trying to formulate an equation that will help us to perform calculations on Arrhenius equation for any given reaction that has two sets of conditions, whereby we have two different rate constants and two different temperatures. So this Arrhenius equation, log k, replace k with k1 for the first set of condition, then log a minus ea all over 2.30, then replace t with t1. That becomes equation 1 for the first set of condition. Also, we will also write similar equation log k to the second set of condition, log k to equal to log a minus ea all over 2.303 r, replace t with t2, to become equation 2 for any given reaction that have two sets of condition or two experimental data differing in their values of k and the values of temperature. Then subtract equation 1 from equation 2. Subtract equation 1 from equation 2. Let's first subtract the left hand side, log k1 and log k2. We have log k2 minus log k1. Then let's go to the right hand side. Subtract log a from log a because the collision factor remains the same. So we now have the right hand side log a minus log a. Then remaining part of the right hand side is minus ea over 2.30 RT2, and for equation 1 minus ea all over 2.303 T1. We subtract the two values, we have minus ea all over 2.30 RT2 minus ea all over 2.30 RT1. So you know the rules in logarithm. When two numbers are, two log values are with the same base are subtracting, you divide. So log k2 minus log k1 becomes log k2 over k1, bringing them to the same log, the same base. Log a minus log a, same thing as saying log a all over log a on the same base. Then we now have the other side that doesn't have log. Minus ea all over 2.30 RT2, you can see it down. Then minus ea all over 2.303 RT1 brought down. So having done that, log k2 over k1 will continue equal to log a over a will vanish. So log a over a gives log 1, and log 1 is 0. So log a over a is cancelled off. So we now have minus ea all over 2.30 RT2. Then minus here will now become plus ea all over 2.303 RT1. So minus up, coming down becomes plus. So you have the expression obtained there, or the equation obtained. Then the next we do is we rearrange the right hand side of the above equation. The right hand side of the equation, the side that has minus EA all over 2.303 RT2 plus EA all over 2.303 RT1. Rearrange it. How do I arrange it? Rearrange it will bring minus EA all over 2.303 RT1 first. You can see that. I will move. So we bring plus EA all over 2.303 RT1 first on the right hand side. Then minus EA all over 2.30 RT2 is shifted. That's the rearrangement we did. You see the same thing. So now I have log K2 over K1 equal to EA all over 2.303 RT1 minus EA all over 2.303 RT2. So having done that, we factorize the right hand side of the above equation. You go to the right hand side, you see that both terms have EA all over 2.303 R on both expressions on the right hand side. You bring it out. So we now have log K2 over K1 equal to EA all over 2.303 R, bracket opens, all over T1 minus 1 over T2. We now take LCM on the right hand side. The LCM of those numbers in bracket is T1 times T2. You bring them under the same denominator and solve. We now have log K2 over K1 equal to EA all over 2.303 R, bracket opens, T2 minus T1 as numerator, bracket closes, all over T1 times T2. That becomes equation 3. So this equation 3 is applied in solving problems involving Arrhenius rate law. You see, equation 3 is used to solve problems on Arrhenius equations involving two temperatures and two rate constants. Let's look at the calculations on Arrhenius problems. Example 1 says the activation energy of the reaction between phosphine and diborane at 298 Kelvin is 48.0 kilojoule per mole. At what temperature would the reaction rate be doubled? And then in bracket you have the gas constant R, capital R, as 8.314 joule per mole per Kelvin. Repeat the question. The activation energy of the reaction between phosphine and diborane at 298 Kelvin is 48.0 kilojoule per mole. At what temperature would the reaction rate be doubled? R is giving us 8.314 joule per mole per Kelvin. Let's go to the solution. The first temperature given to us is 298 Kelvin, so that's our T1, 298 Kelvin. The gas constant 8.314 joule per mole per Kelvin given to us already in the bracket. The additional energy is given to us as 48.0 kilojoule per mole. Write it out. EA 48.0 kilojoule per mole per Kelvin. How to convert that additional energy to joules? Why do we convert to joules? Look at the unit of the gas constant, 8.314 joule per mole per Kelvin. And look at the unit of the additional energy, carrying kilojoules. So kilojoule and joules and joule is not uniform. So we need to convert either the joule to kilojoule or convert the kilojoules to joule. So in this work, we have to convert the kilojoule to joule. So the units become uniform. So how to convert kilojoule to joule? We multiply by 1000. We now have 48 times power 3 joule per mole, because 1 kilojoule is equal to 1000 joules. So to make the units uniform. So we're looking for T2, the temperature, the second temperature. So as they say, at what temperature would the reaction rate be doubled? So we're looking for T2. So we'll go ahead. For the reaction rate to be doubled, it means that K2 will be equal to 2K1. That the rate constant, the new rate constant is going to be double the initial rate constant, and that will double the rate of reaction. So we'll go to equation 3 that we obtained previously by joining two sets of condition with the Arrhenius equation. Log K2 over K1 equal to EA all over 2.30 R, bracket opens, T2 minus T1 all over T1 times T2. That's the equation 3 we derived before now. So having gotten this, we now substitute the values we have. So for the reaction rate to be doubled, as I said, so K2 is going to be equal to 2K1. To replace K2 with 2K1, so replace K2 with 2K1, as you can see there, and then K1 under. Then our EA, which is fusion energy, remember we have done the conversion, is 48 times 10 power 3 joule per mole. Replace EA with 48 times power 3. Then 2.303 under. Then the gas constant, which is 8.314. We're looking for T2. The value of T2 is unknown. T1, the initial temperature given to us at 298, so we have T2 minus 298 all over. T1 is 298 under 298 times T2. So this is what we have after substitution. Having done that, K1 cancels K1. We are now left under with log 2 equal to, when we solve on the right hand side, 48 times power 3 all over 2.303 power 8 times 8.314. So when we solve that expression before the bracket, 48 times 10 power 3 over 2.303 times 8.314, we obtain 2506.9 under 2506.9. Then the bracket, the values are still intact. In the bracket, have T2 minus 298 all over 298 multiplied by T2. So we'll divide both sides by 2506.9. Divide both sides by 2506.9. So that 2506.9 will be removed from the right hand side. So removing the thing, we now have T2 minus 298 all over 298 T2, because if you divide 2506.9 by the same 2506.9, you get 1 to vanish. So right hand side will now be T2 all over T2 minus 98 minus 298 all over 298 multiplied by T2. So you're left with what you have inside the bracket now. So the left hand side log 2. Log 2 is 0.3010 divided by 2506.9. So log 2, the value is 0.3010 divided by 2506.9. So when you divide 0.3010 by 2506.9 on the left hand side, you're going to get 1.201 times power minus 4. And the right hand side remains intact, T2 minus 298 numerator all over 298 T2 denominator. We'll now cross multiply. Multiply the numerator on the left hand side, that is 1.201 to power minus 4, by the denominator on the right hand side, that is 298 T2, and multiply the numerator on the right hand side, T2 minus 298, by 1 with the denominator on the left hand side. So we'll have that expression done. So when you multiply 1.201 to the power minus 4 multiplied by 298 T2 will now give us 0.03571 T2. We multiply the left hand side equal to T2 minus 298. We'll now collect like terms. How to collect like terms? The values carrying T2 move them to one side. So we now have 0.3571 T2 minus T2 going over to the left hand side, remaining on the right hand side. We now have minus 298 remaining on the right hand side. So 0.3571 T2 minus T2, subtract the coefficient, that is 0.3571 minus 1. That gives you 0.3571. minus 0.96424 minus 0.96424. So minus 0.96424 T2. Okay, then the right hand side remains minus 298. We want to make T to the subject. Divide both sides by minus 0.96424. So we now have 298 minus the minus we cancel on both sides. So T2 now becomes 298 all over 0.96424. And that will give us 309.1 Kelvin. 309.1 Kelvin at the temperature we're looking for. Example 2 says benzene diazonin chloride decomposes in the presence of water according to the first order kinetics. If the velocity constant at 25 degrees Celsius is 2.8 times per minus 3 per minute, and the activation energy is 11.9 kilocal per mole. Find the velocity constant at 35 degrees Celsius. Take R to be equal to 1.987 kilocal per mole. There go the solution. So solution we have to list what's given to us. We have to list out the values given to us. So our EA, which is the activation energy, is 11.9 kilocal. You can see it's given to you 11.9 kilocal per mole. So our R is given to us as 1.987 kilocal per mole. Look at this problem. The EA is expressed in calories, kilocalories per mole, and then the arrow is given to us also in kilocalories per mole. You see that the units are uniform. We have uniform units here. So I think that the EA is in joules, like in the previous example. The EA is in joules per mole. So I repeat, had it been that the unit of activation energy EA is in joule per mole per Kelvin, so the unit of R would also be in joule per mole per Kelvin, and then the value of R wouldn't have been 1.987, rather would have been the SI unit value, which is 8.314. But since the EA was kept in a non-SI unit, so the R must also correspond to it. So our temperature, or the first temperature, is 25 degrees Celsius. You can see it there. We correspond to the rate constant of 2.8 per minus 3. So that 25 degrees Celsius becomes our T1. We'll convert to Kelvin by adding 273, and that will give us 298 Kelvin. Our second temperature given to us is 35 degrees Celsius. And we have to find a velocity constant at 35 degrees Celsius. So 35 becomes our T2. Both convert to Kelvin by adding 273. That becomes 308 Kelvin. Our K1, which is the rate constant that corresponds to 25 degrees Celsius, which is 2.8 per minus 3 per minute. So our K1 is 2.3 per minus 3 per minute. Our K2 is what we're looking for. So we have to find a velocity constant at 35 degrees. That's our K2. We still employ equation 3 we derived above. Log K2 over K1 equal to EA all over 2.30 R. Bracket opens, T2 minus T1 on the numerator all over T1 times T2 as denominator. So we substitute the values given to us. We don't know K2, so we leave K2 unsubstituted. Log K2 all over K1 is 2.8 per minus 3. Then our EA, that activation energy, is 11.9. So we substitute EA with 11.9 all over 2.303, which is part of the formula, times R, that the gas constant in kilocal, that is 1.987, all over T2, which is 308, 35 degrees in Kelvin is 308, minus T1, 25 degrees in Kelvin is 298. So 308 minus 298 all over T1 times T2, which is 308 times 298. So, solving out, we now apply the law of logarithm. The division law can also change to separating the log. It change to subtraction. So now have log k2 minus log 2.8 to the power minus 3, separating the logs with subtraction, equal to, then the numerator is on the right hand side 1.19 divided by 2.303 times power times 1.987. I repeat myself, 11.9, not 1.1, 11.9 divided by 2.303 times 1.987 will give us 2.60. Then the 1 in bracket, 308 minus 298. 308 minus 298 will give us 10. Then divide the 10 by 308 multiplied by 298. Divide the numerator, if you saw the numerator in bracket, you get 10. Divide it by the product of 308 and 298, you get 1.09 times power minus 4. So we'll continue. Log k2 equal to log k2 minus, then log 2.8 power minus 3 will give us minus 2.553 in bracket. Then we'll multiply 2.60 by 1.09 to the power minus 4, and that will give us 2.834 to the power minus 4 on the right hand side. So solving, log k2 minus outside multiplied by the minus inside the bracket on the left hand side. Minus times minus will give you plus. We now have log k2 plus 2.553 equal to 2.834 times power minus 4. So we'll collect items. Log k2 equal to, move 2.553 to the right hand side, it turns to minus. So we now have 2.834 times power minus 4 minus 2.553 on the right hand side. So log k2 becomes minus 2.553. So what am I saying? 2.834 to power minus 4 minus 2.553 will give us negative 2.553. So log k2 equal to negative 2.553. We're looking for k2. We'll take anti-log on both sides. So k2 becomes anti-log of minus 2.553. So k2 becomes 2.799 times power minus 3 per minute as our k2. Go to example 3. Example 3 says the colorless gas dinitrogen tetraoxide N2O4 decomposes to reddish brown NO2 in a first order kinetics with a value of K of 4.5 times power 3 per second at 274 Kelvin. If K is 1.00 times power 4 per second at 283 Kelvin, calculate the energy of activation. Take R to be equal to 8.314 joule per mole per Kelvin. Repeat the question again. The colorless gas dinitrogen tetraoxide N2O4 decomposes to the reddish brown gas NO2 in a first order kinetics with a value of K of 4.5 times power 3 per second at 274 Kelvin. If K, that the rate constant, is 1.00 times power 4 per second at 283 Kelvin, calculate the energy of activation. Take R to be equal to 8.314 joule per mole per Kelvin. Go to the solution. Our T1 is 274 Kelvin. That's our T1. Our K1, which is the first velocity or rate constant, is 4.5 times power 3 per second. So that look at 224 Kelvin corresponds to the constant 4.5 times power 3 per second. So our T1 is 224, while K1 is 4.5 times power 3 per second. Our T2 is current temperature, which is 283 Kelvin. Our K2, the corresponding velocity or rate constant, which is 1.00 to the power 4 per second. You go to the equation, you can see our T2 as 283 Kelvin. You can see it there. And the corresponding velocity constant is 1.00 to the power 4 per second. So we have done that. We are now looking for, they gave us R as 8.314 joule per mole per Kelvin. We're looking for the activation energy. We still apply same equation 3 that says log K2 over K1 equal to EA all over 2.303 R, bracket opens, T2 minus T1 as numerator all over T1 times T2 as denominator. So we'll now make a substitution with the given values. So the value of K2 is 1.00 times power 4. Our K1 is 4.5 times power 3 equal to EA, which we're looking for, all over 2.303, part of the formula, times R. This one around our R is 8.314. Then bracket opens, our T2 is 283 and our T1 is 274. So subtract 283 minus 274 all over 283 times 274. So solving, we now divide 1.00 times power 4 by 4.5 times power 3. We divide that, we have 2.222 log 2.222 equal to EA. We multiply the denominator 2.303 by 8.314. We obtain 19.5 under. Then we solve the ones in bracket. 283 minus 274. 283 minus 274 will give us 9. Then divide 9 by the product of 283 and 274. We'll have 1.16 times power minus 4. So having done that, we'll then cross multiply, move 19.15 to the left hand side by cross multiplication. So we now have 19.15 times log 2.22, that is 222. I have to correct the error, that is 2.222, 222 should be there. Okay, equal to log, equal to EA, the right hand side, EA bracket opens, 1.16, that power minus 4. So when we solve 19.15 multiplied by log 2.222 give us 6.640 equal to EA multiplied by 1.16 power minus 4 on the right hand side. So make EA the subject by dividing both sides by 1.16 power minus 4 to make EA the subject. So EA becomes 6.640 all over 1.16 power minus 4, and that will give us 5.72 times 10 power 4 joule per mole as our activation energy. So this brings the lecture to an end on Arrhenius rate equation and its application in solving problems whereby you're given two temperatures and two different specific rate constant or velocity constant for a given reaction. So stay connected, share our videos. If you're not subscribed to the channel, tap on the channel's button or tiny bell to get subscribed, share our videos, and then make your comments. Thank you for listening. Thank you very much.